Hello friends, welcome back to another lecture on speech. If you recall, the last class I spoke about separating out the effect of the speech production can be thought of as two parts to it. There's an excitation, and then there's a filter, which is basically the mouth that manipulates the resonant frequencies, and the speech signal comes out, right? So if you recall, for the last few classes we first talked about the production part, and then we talked about the hearing, the listening part, right, the perception part of it. Then now we have come back to the speech part of it, the production part, and now we will worry about how we will use the speech signal to do many useful things with it, okay? Speech recognition, many other things. So first I'll talk about something called the Mel Frequency Cepstral Coefficients, which is very important set of features that are often used in many applications in speech technology. And then I also have to deal with the statistical aspects and so on, so give you background on that. So these will be the sort of things we will cover in the next few classes, okay? So I'm using a term called spectrum, it's a cepstrum, so it's a play on the word spectrum. I will come to why we talk about it. In fact, last class I had already told you that we talk about filtering, spectral analysis. Spectral analysis means analysis of frequency. That's why we talk about the spectrum, right? I mean, light spectrum, so many things we talk about, right? And cepstrum is a play on that same thing. Spec becomes cepstrum, okay? And the reason is we do similar kind of ideas, but not in the time domain, but in the frequency domain, okay? So just to remind you, so we have the production model that has some vibrations or resonance, I mean impulses that happen, or noise like when f, sat, hat, right? And then there is the mouth that actually has these resonant frequencies. Each phoneme or each basic sound unit that we have in our language has typical resonant frequencies which are different from other sound units, okay? And therefore when you do this filtering idea, it involves a multiplication in the frequency domain, right? So this waveform in the frequency gets multiplied by this function in frequency to give you the output signal S of t, whose Fourier transform is what I am showing here. It is a multiplication of these two, okay? So the basic idea is that given we can only measure the speech signal, right? So given this, if I am interested in only finding out what is the V of omega, right, the mouth aspects of it, how do I extract that information, right? And one good thing, if you notice, and if you recall from previous class, I had mentioned this is slowly varying and this is rapidly varying. It goes to 1 0 1 0 or whatever, some high value 0, high value 0. So this is a rapidly varying signal, this is a slowly varying signal, and by applying a log on the magnitude, we are only reducing the dynamic range, we don't change anything. The shape is still remains the same, it's just the dynamic range reduces. But log has another important property, multiplication, a times b, right? If I apply a log of a times b is log a plus log b. So what is multiplicative? So there was some multiplicative thing. S of omega was nothing but v of omega, right? So let me just put the S of omega is nothing but the v of omega multiplied by e of omega. Now by applying a log, one is the dynamic range gets reduced, the other is it becomes a separable quantity, it becomes additive, right? And then we know that if there is a slowly varying signal and a rapidly varying signal, then that concept of averaging, low pass filtering can be used to extract the low frequency parts, right? And that is the principle which we are going to use here, okay? So what is the task? We would like to separate out the vocal tract information given only the speech signal, right? So we don't have separately the access to these two, we only have the access to the rarefactions and compressions which a microphone might have picked up, and the waveform then we did an analog to digital conversion, we have it on the computer now, right? So what do we do, right? So just to recall from whatever I told you in the previous class, just revising 2 minutes. So if I have a signal that has some signal of interest and some noise here, noise means something that is not of interest, and I am interested only in capturing this guy, okay. And we know this is all in the frequency domain. We can use a filter. This is a low pass filter because it's passing only the low frequencies. That's why it's called a low pass filter, and I'll get back the signal, right? And so there's no noise. So essentially, I have separated out the noise and got back the signal. So I've removed the effects of the noise. The same idea we are now going to do to separate out the excitation effects from the vocal tract effects. But there it was multiplicative, so I have to apply this concept of log. Okay. So two things happen. So one principle is convolution in time domain becomes multiplication in frequency domain. So now the vocal tract frequency response is multiplied by the excitation frequency response. That I am now going to make it additive by applying a log operation. And another property is the vocal tract is slowly varying in the frequency domain, it has the envelope, and the excitation is rapidly varying, right? And so we have to filter it, but because we are operating in this frequency domain and not in the time domain, in time domain we like to use the word filter. When I am doing something in the frequency domain, we want to remind the user that you are doing it in a different domain. So historically people have used a slightly different term. They use it, call it liftering rather than filtering, okay. So the basic idea here is very simple. This is my speech signal, which is here it is multiplication. This term is actually should be multiplication, okay, not convolution. So the symbol used here is wrong. So this is multiplication, okay, and therefore when I apply the log, it should be magnitude, right? I mean, because complex quantities are difficult to deal with. So here we are talking about magnitudes, and in speech magnitude of frequency response is more than enough. Even if you lose a phase information, often it is not very harmful. So it's log of E of omega and log of magnitude of V of omega, right? So this is beautiful. So this is similar to what I had discussed last class. I am actually having access to only log of S of omega. That's just the amplitude which reduces the dynamic range by applying log. But now it becomes additive. There is a slow, rapidly varying part, which is a log of the excitation frequency response, and the vocal tract frequency response, which is slowly varying, right? And so my interest is, given this guy, can I get back the slowly varying part, right? And we said that that is possible by using a moving average filter, but in this case we will use a simple moving average lifter. That is the only idea that we are going to do here, okay? And that is a very important idea and quite extensively used, so I will talk about it. So if you look at the cepstrum, remember cepstrum is nothing but log of S of omega, that is all I have done, okay? So I have come into the log of S of omega, and then if I look in the frequency in the do a Fourier transform, you will see that the low pass part is here, right, and the high pass parts are here. You cannot see it very clearly, but this is actually the vocal tract response, and these are what we call as the excitation responses, okay. So I use a lifter here, okay, and this lifter if I do, then in the frequency domain you will see, if I only take this part and come back into the frequency domain, you will see the original signal was rapidly varying. That is the original log of S of omega. So that wavy curve that you saw here, right? So this lots of rapidly varying thing is log of S of omega, and the slowly varying after doing this liftering operation, if you look back, I get the envelope very nicely. This is log of V of omega. If you look at the dot, red dot that I am doing, that solid curve, that is coming beautifully capturing the envelope. So this is a very simple way to separate out the excitation from the vocal tract, okay. This is liftering by going into the cepstral domain, but I said an easier way is to just do averaging, right? In the so that averaging is done by using this idea of triangular averaging, okay. So instead of doing rectangular averaging, I am doing triangular averaging. So I do this is in the frequency domain, and I take a set of few samples in some localized and then keep moving the average, and this is what we talked about here, the moving average that we talked about here. Okay. So this is the simple idea that I am going to do. So if you go back to the previous class and look at my notes where I said ZT, XT and noise, and how from ZT I got X of t, the same thing, but now the t variable has got changed into omega variable, and instead of Z I am calling it as S, instead of X I am calling it as V, instead of noise I am calling it as E of omega. That's the only difference. The ideas are very similar. There I used a simple rectangular averaging. In practice, in most of speech operations, historically we have used triangular averaging. That's there's nothing great about it. It just happens to be that we have always consistently used triangle. So we'll continue in the future also. So this is some kind of an established way of doing things. Okay. So, but the idea is very clear to you, I hope, right? So now I will talk about why are we interested in this idea, right? There are many reasons why we want to do this. One of the reasons is we want to extract. Speech has lot of information. It has information about gender, it has information about emotion, it has information about what you are saying, right? I mean, that's the information content that I'm talking about, right? And on top of it, also we can easily perceive the age to some extent, right? Average, is he very old or young? You can easily make out child, right? You can easily make out, you can make out the gender, you can make out the emotional state, is he angry, sad, so many things. So speech has lots of information. Usually that is not easily captured in text, right? In text, it's inanimate, right? There is no life in it, right? You can't even make out whether the guy was angry or sad, right? Unless you write, nowadays we write in capital letters to say we are angry or we want to emphasize something, right? But by and large, speech has a lot of this other information that's very useful. Okay. So what, instead of having all this information, when we are doing some kind of a pattern classification, pattern recognition kind of problems, right? We want to extract something useful from the signal. We want to ignore all other things that are not relevant and only capture things that are useful. So typically the term we use is we want to extract features that are relevant to that particular problem. Okay. So now we are slowly moving how to take the speech signal that has already come out from the speech production process and use that speech signal towards doing something useful. So that is the direction in which we are going. Okay. So that means that if you look at this, we are going to be talking about something called features. Typically, there are two broad aspects we will talk about. One is called the Mel filter bank features. Okay, I'll come. That Mel is missing here. That's a very important part. And the other is a slightly older. Nowadays, also people use, but this is called Mel Frequency Cepstral Coefficient. So the MFCC is full form is Mel Frequency Cepstral Coefficient, and it should be MFB or Mel filter bank. Okay. And in today's deep learning methods, we use Mel filter bank. We will see that because we can handle correlations. But historically, for last, before the deep learning kind of ideas came through, we were using statistical ideas and Gaussian method, models, and therefore diagonal covariance was very important. And so the MFCC was what that was historically used for about 40-50 years. Okay, it's only of late, at least 35 years. It's only of late that people have gone to Mel filter bank. Okay, so what is this Mel filter bank, right? So, so as I said, the basic idea in Mel filter bank is very simple. You are given a speech signal, right? You are going to take the speech signal and now try to get the envelope, the V of omega, the voice, vocal part of it, the vocal tract part of it. And so the steps that you normally do are these three steps that we talked about here. So we take the speech signal, we convert it into frequency, and remember in computers we use the DFT as a Fourier representation, and then we take the log. Remember, why do we take the log? We want the multiplicative aspects in the frequency to become additive aspects, and then we do the low pass filtering, which, because we are in the frequency domain, the term we use is liftering, and extract that part. That is what we call as the Mel filter bank. And so the averaging to get the low pass part is done by this set of triangle filters. Now, what you should notice here is that these triangular filters are not equally spaced and they are not of equal bandwidth. This becomes very, very important. Why are we doing this? So you can see that the bandwidth means the the duration of the filter in the frequency, right? In the lower parts it's very, very narrow, and then slowly when I come to the 4000 hertz it's very wide, right? It's a big triangle, right? It's occupying a larger frequency region. Secondly, you will also notice that the peaks of the filters, they are close by when I am in the low frequency and they are further apart when I am in the high frequency. Why do we do this? The reason is, this, remember, is the physical frequency, right? But we know that the ear operates in the Mel domain, okay, the Mel frequency. And what is the relationship between the physical frequency and the Mel frequency? There's actually a good mathematical fit to it. So Mel is equal to, Mel's the quantity is equal to 1125 ln of 1 plus physical frequency f by 700. That is the mathematical relationship. And what we are trying to do is, because the ear is so good and so it must be doing something, there must be some intelligence. Why is it using this Mel? So why not we also use Mel in our processing rather than physical frequency? Therefore, we convert the physical frequency hertz into Mel frequency. So it is just some conversion of some conversion of the axis to mimic what the ear does. So we feel that the ear is must be a good thing, right? We are the best speech recognizers, processors, right? So human listeners are the best. So machines are only trying to mimic or imitate them. So why not do that, right? And they did that and they got good performance. So that is why we stick with it, right? So we tried it. Some guys, Davis and Mermelstein, tried it in 1980 and it worked very well. And then for next 42 years, we have been using the same thing, okay? So there, they found that using Mel scale instead of the physical frequency scale works well. So actually we want to do the liftering or the smooth averaging, triangular averaging in the Mel domain. In the Mel domain it will be equally spaced with equal bandwidth, okay. But when we come back into the physical frequency, right here, these become non-uniform, they are non-uniformly spaced and they have non-uniform bandwidth. This is almost like something called the constant Q property. That is, the ratio of the width of the filter to the center frequency is almost a constant, right? So this constant Q is often used by many sensory, many human aspects of processing, and so that seems to be somehow the nature tries to prefers that to a big extent, and that is why it looks funny the way the filters are drawn here. They are not uniformly spaced, neither do they have uniform bandwidth. The reason is we are always trying to mimic the ear, and the ear operates only in the Mel domain. So actually these are operating in equally spaced, equal bandwidth in the Mel domain, and it is trying to remove the effects of the voicing and try to extract the envelope information, which is more related to the sound that we produce, okay. So now if you are clear, that is why the term Mel becomes very important now. So actually we are doing everything in the Mel, we want to do everything in the Mel domain, but in practice we are operating, we use the physical frequency hertz, on the computers to do our processing, and therefore there is this relationship, that's all, okay. So this is actually doing something in the Mel domain, okay. But instead of doing that, we do an equivalent operation in the frequency domain, okay. So ultimate idea is always Mel. So that's why the term Mel should be always preserved. So it should be Mel filter bank. So this is not a typical filter bank. This is called the Mel filter bank, okay. So this is Mel filter bank, and after the averaging, normally we use a log operation to reduce the dynamic range. So the term that we often use is log Mel filter bank, okay. Log is applied after the averaging operation. Why do we do the averaging operation? To remove the effects of the excitation and capture more on the frequency of the vocal tract, okay, the resonant frequencies. So now we have this term log Mel filter bank. What are these MFCCs? Where have they come from? Okay, this again is historical. Nowadays, not many of us use, at least in deep learning methods. Why did this idea of Mel frequency Cepstral coefficients come? Okay, so the reason is we don't stop here. Okay, we could use these as features. This is basically already filtered and only the vocal tract information is there. But if we were using conventional classical statistical methods like a mixture of Gaussians, I'll come to it in the next next class. Therefore, in the idea of Gaussian, we have this concept of something called covariance matrices, and we prefer something called diagonal covariances simply because we want those features, I mean, that the number of parameters reduces tremendously. These are square matrices where, of course, because of the symmetry of the covariance matrices, 1/2 is only necessary, but still the number of parameters in a full covariance matrix is very large. Okay, and data is always a big problem in all of our pattern recognition problems. Okay, therefore they usually use diagonal covariances, which means there is an assumption that the features are uncorrelated. Now, I'm not going to go too much into the fact of what is uncorrelated versus correlated. I'll just give you some flavor to it, but I'm sure you would have covered somewhere in one of the basic math courses that have been covered as a part of this whole course. Okay, so here all that I'm trying to say is, in the olden days we were worried about decorrelating the features, that the features should not have too much dependence on each other in some sense. And if you look at this, if I look at the output of all of these, there is a quite a significant overlap between these filters, right? And therefore, consecutive, if I look at the outputs of these things, there is some relationship. They are not going to abruptly change like noise, right? So if I have the output of this filter, I know that the output of the next filter will be somewhat related to it, right? It won't randomly go at some negative value or somewhere really far away, right? So there is this variation that is quite slow, and therefore we can see there's a high correlation between consecutive samples or outputs of the filter bank. Okay, and this was a big problem because that means this, if I take the outputs of these filters, these features will be highly correlated. So we need something to decorrelate them. The idea is basically like something like a Gram-Schmidt, right, where we have linearly independent vectors, right? So they are not orthogonal, but they are independent of each other. We would like to orthogonalize them in some sense, right? And that once you orthogonalize something, then it becomes very easy to compute the coefficients of the linear combination and so on. And similarly, we could decorrelate features also by using a decorrelating transform. But what Pohls found, one of the good scientists of the 70s, that there is a simple transform, like how we had the Fourier transform. There is a transform called discrete cosine transform. In fact, there are a set of 8 transforms, DCT1, DCT2, and then the discrete sine transforms and so on. Okay, but the idea is that this discrete cosine transform is somewhat cosine, right? Somewhat like Fourier transform. Remember, in Fourier transform, the basis functions are e to the power of j omega, right? And from this thing we know it's cos omega plus j sine omega, right? In the cosine transform, only the cosine aspects of it come into picture. So this is a transform where the basis functions are in terms of cosine. Okay, but Pohls found that this DCT2 quite dramatically decorrelates the filter bank features. Okay, so therefore we use this cosine DCT2 discrete cosine transform to, and this, by the way, this is also heavily used in image processing. All or many of the standards like the MP4 standards, all of them, they have somewhere a DCT coming into picture. Okay, or modified version of it, modified DCT, right? And so we are going to decorrelate this feature using a DCT2, which is some kind of a, not a Fourier transform, but similar to a Fourier transform, where the basis functions are cosine, and then extract the feature. Okay, so that is why the term that we use is called Mel Frequency Cepstral Coefficients, which is nothing but the filter bank coefficients with a DCT operation applied to get the Mel Frequency Cepstral Coefficients. Okay, and then we do something called delta and delta delta. I'll come to that.